Look up at the night sky, really look at it, and tell me what you see. A scattering of stars, maybe the moon, a few distant pinpricks of light against the endless dark. But here's the thing, what you're seeing is just the tiniest fraction of what's actually out there. The universe is so vast, so unimaginably enormous, that our brains can't even begin to comprehend its scale. And yet, for all its size, it's not empty. It's alive with mysteries, strange, beautiful, and sometimes terrifying phenomena that defy everything we think we know. Black holes that warp time itself, galaxies spinning at impossible speeds, dark energy tearing the cosmos apart at the seams. These aren't just abstract ideas or sci-fi concepts. They're real, they're happening right now, and they're shaping the very fabric of reality. Think about that for a second. Every time you glance up at the stars, you're looking at a universe filled with questions we still can't answer. Why is everything expanding faster and faster? What lurks in the void between galaxies? Are we alone, or is there something or someone else out there? These aren't just scientific puzzles, they're deep, existential wonders that have haunted humanity for centuries. And today, we're diving headfirst into 25 of the most mind-bending mysteries the cosmos has to offer. From the eerie silence of Fermi's paradox to the ghostly whispers of dark matter, we'll explore the edges of human understanding and stare into the abyss of what we still don't know. This isn't just a tour of cool space facts. It's a journey to the frontiers of discovery, where the rules of physics start to break down and the universe reveals its strangest secrets. Imagine standing at the edge of a black hole where time slows to a crawl. Picture a galaxy made entirely of antimatter, lurking undetected in the cosmic dark. These aren't fantasies, they're real possibilities scientists are grappling with right now. And whether you're a casual stargazer or a hardcore science fan, these mysteries will leave you with one overwhelming feeling: wonder. Because the more we learn about the universe, the more we realize how much we've yet to discover. So buckle up. We're about to take a ride through the cosmos, and trust me, you won't believe what's waiting for us out there. One of the most baffling discoveries in modern cosmology is this: the universe isn't just expanding, it's speeding up. Think of it like a car rolling downhill, only instead of slowing down, it inexplicably hits the gas pedal harder and harder over time. This wasn't what scientists expected at all. For decades, the assumption was that gravity, the relentless pull of all the matter in the cosmos, would eventually slow the expansion, maybe even reverse it. But in the late 1990s, two separate teams studying distant supernova made a shocking observation. These exploding stars, used as cosmic mile markers, were fainter than they should have been. The only explanation: the space between us and them was stretching faster than anyone predicted. That's where dark energy enters the picture, a mysterious force making up roughly 68% of the universe, yet we have no idea what it actually is. It behaves like a kind of anti-gravity, pushing galaxies apart instead of pulling them together. The leading theory points to something called the cosmological constant, an idea Einstein once dismissed as his greatest blunder. But here's the twist: when scientists calculate how much energy this constant should contain, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, not even close. What makes this so unsettling is how it upends our understanding of physics. Dark energy shouldn't exist at this magnitude. Yet, every observation confirms it's out there, relentlessly stretching the fabric of space. Some suggest it's tied to quantum fluctuations in the vacuum of space itself, a sea of particles constantly popping in and out of existence. Others propose entirely new laws of physics, but the truth: we're grasping at shadows. If this acceleration continues unchecked, distant galaxies will eventually vanish from view, their light stretched beyond detection. The cosmos could end not with a bang, but with a silent, icy drift into darkness. But while dark energy pulls the universe apart, another invisible force holds it together: dark matter. Picture a galaxy spinning like a giant cosmic pinwheel. According to the laws of physics as we know them, stars on the outer edges should move slower than those near the center, just like planets farther from the sun orbit more sluggishly. But here's the catch: they don't. Observations show stars at the edges of galaxies whipping around just as fast as those closer in, as if some unseen hand were gripping them, keeping them from flying off into space. That hand is dark matter, an invisible substance that outweighs ordinary matter by a factor of 5 to 1, yet refuses to reveal itself beyond its gravitational shadow. The evidence doesn't stop there. Look at the way massive galaxy clusters bend light around them like cosmic magnifying glasses, a phenomenon called gravitational lensing. The amount of bending we see requires far more mass than the visible stars and gas can account for. It's as if the universe is draped with an enormous, unseen scaffold, a hidden architecture shaping everything we observe. Even the way galaxies clump together in vast cosmic webs points to dark matter's influence. Without it, the universe as we know it wouldn't exist. Yet after decades of hunting, we still don't know what dark matter actually is. The leading candidates range from weakly interacting massive particles, WIMP hypothetical heavy particles that barely interact with normal matter, to actions, ultralight particles streaming through space like an invisible fog. Some experiments have reported tantalizing hints, like the faint, unexplained signal in the xenon detector deep beneath an Italian mountain, but nothing conclusive. Others have turned up empty-handed, leaving scientists scratching their heads. The frustration is real. We're surrounded by this stuff every second. Billions of dark matter particles might be passing right through your body, yet it's as elusive as a whisper in a hurricane. Some theorists have even begun questioning whether we're chasing a phantom, proposing instead that gravity itself behaves differently on cosmic scales. But if dark matter is real, and if we ever manage to catch it, it would rewrite the story of the universe. Imagine handing a detective a case where the suspect leaves fingerprints everywhere but is utterly invisible. That's the puzzle of dark matter, a cosmic enigma hiding in plain sight. Imagine the universe isn't just a scattering of isolated galaxies, but a vast, intricate tapestry, threads of matter stretching billions of light years, weaving a structure so immense it dwarfs even the grandest cosmic landmarks. This is the cosmic web, the hidden skeleton of the universe. At its largest scale, everything stars, galaxies, galaxy clusters is connected by enormous filaments of dark matter and gas, forming a pattern reminiscent of neurons in a brain or veins in a leaf. But how does something so delicate-looking govern the entire cosmos? The answer lies in the aftermath of the Big Bang. Tiny quantum fluctuations, smaller than an atom, were stretched to cosmic proportions as the universe expanded. These minuscule wrinkles in space-time became the seeds for the web's structure, with gravity amplifying them over billions of years. Dark matter, invisible and mysterious, acted as the scaffolding, its gravitational pull drawing ordinary matter into dense nodes and thread-like filaments. The galaxies we see today, they're just the glittering beads strung along these invisible threads. Yet here's where things get strange. When scientists simulate the universe's growth using supercomputers, their models produce a cosmic web, but not quite the one we observe. The real thing is more intricate, with finer filaments and more pronounced voids than simulations predict. It's as if something's missing from the equations. Some suggest undiscovered properties of dark matter might be at play, like interactions beyond gravity. Others wonder if dark energy, stretching space itself, is subtly reshaping the web over time. The most striking feature of this cosmic architecture, its voids. These enormous, nearly empty regions span hundreds of millions of light years, yet their boundaries are razor-sharp, lined with galaxies like foam on ocean waves. How such vast emptiness forms, and why matter clumps so precisely around it, remains one of the web's deepest puzzles. What's clear is that this isn't random chaos, it's a meticulously organized structure, written in the language of gravity and shadow. And until we crack its code, the universe's grand design will keep its secrets. Here's something that might surprise you. We can't even find half the ordinary matter in the universe. Not dark matter, not exotic particles, but the stuff we're made of: protons, neutrons, electrons, the atoms that form planets, stars, and even you. Scientists call this the missing baryon problem, and it's one of those quiet cosmic embarrassments. We know roughly how much ordinary matter should exist based on the afterglow of the Big Bang, the cosmic microwave background. But when we tally up all the visible galaxies, gas clouds, and dust, nearly half of it's just gone. So where is it hiding? The leading suspect is something called the warm-hot intergalactic medium, or WIM, a ghostly web of superheated gas strung between galaxies. Picture steam so thin it's practically invisible, but so vast it could wrap around the universe. This gas isn't cold and dense like the clouds where stars are born. It's scorching, 1,000,000 degrees or more, and so diffuse that a cubic meter of it might hold just a few atoms. That makes it nearly impossible to see with traditional telescopes. But every so often we catch glimpses, when distant quasars, those blazing cores of ancient galaxies, shine their light through the cosmos. The WIM leaves faint fingerprints. Specific wavelengths of light get absorbed, revealing the presence of heavy elements like oxygen and nitrogen. It's like finding a single glowing thread in a pitch-black room. Even with these clues, the math still doesn't quite add up. Some of the missing matter might be lurking in even stranger places, like the halos of galaxies where it's too dim to spot. Or perhaps it's tied up in vast, undetected reservoirs of cold gas floating in the voids between cosmic filaments. There's even a wilder idea: tiny primordial black holes, forged in the chaos of the early universe, could be hoarding matter like invisible cosmic safes. What's fascinating isn't just the mystery, it's what it says about how little we truly understand the universe's plumbing. We're like detectives reconstructing a crime scene where the suspect left behind only traces of smoke. And until we solve it, we can't even be sure we're reading the cosmic ledger right. If half the ordinary stuff is missing, what else might we have overlooked? Now let's talk about something that shouldn't be, but somehow is. When scientists mapped the cosmic microwave background, that faint afterglow of the Big Bang, they expected randomness. Tiny fluctuations in temperature scattered like debris from an explosion, a cosmic fingerprint with no pattern, no direction, but the universe had other plans. What they found instead was eerily aligned, almost as if the cosmos itself were pointing a finger straight at us. They called it the axis of evil. This isn't some dramatic nickname for effect. The fluctuations in the CMB, those primordial whispers from the dawn of time, show a peculiar correlation with the plane of our solar system. Imagine throwing confetti into the air and watching it fall, only instead of scattering chaotically, it arranges itself into neat lines that just happen to match the tilt of your dining table. That's the level of weird we're dealing with. Statistically, the odds of this alignment happening by chance are astronomically low, like flipping a coin 100 times and getting heads every single time. So what's going on? One possibility is that something in our local environment, maybe the way dust absorbs light or the way our telescopes process data, is creating a false signal. But after years of checking, recalibrating, and launching more precise satellites like Planck, the anomaly stubbornly persists. That leaves the far more unsettling alternative: this might be real. And if it is, it could mean our understanding of the universe is missing a crucial piece. Some theorists suggest this alignment hints at a pre-Big Bang structure, a ghostly imprint of something that existed before time began. Others propose it's evidence of a multiverse, with our universe brushing up against another in ways we can't yet comprehend. The wildest idea: that we're seeing the fingerprints of an entirely new force or field, something beyond the standard model of physics, warping the fabric of reality on cosmic scales. Here's what makes this so deeply unnerving. The cosmic microwave background is supposed to be the ultimate blank slate, a snapshot of the universe before galaxies, before stars, before any structure existed. If it's already whispering secrets we don't understand, what else have we gotten wrong? The axis of evil isn't just a curiosity, it's a cosmic riddle, one that could rewrite the rules of reality itself. If there's one number that should unite all of cosmology, it's the Hubble constant, the rate at which the universe is expanding. But here's the catch, we can't seem to agree on what that number actually is. Imagine two groups of scientists using different rulers to measure the same distance, only to find their answers drifting further apart the more precise their tools become. That's the Hubble tension, and it's throwing modern astrophysics into chaos. The first method relies on the cosmic distance ladder, a step-by-step approach using pulsating stars called cepheids and cataclysmic supernova as mile markers. By measuring how fast galaxies are receding from us, scientists arrive at an expansion rate around 73 kilometers per second per megaparsec. But there's another way to calculate it, by studying the cosmic microwave background, the afterglow of the Big Bang. The Planck satellite's meticulous observations suggest a slower expansion, 67 kilometers per second per megaparsec. At first glance, that difference might seem trivial, but in the precise world of cosmology, it's like discovering your compass points north while your GPS insists it's south. What makes this so unsettling is that both methods are rock solid in their own right. The local measurements cepheids, supernova, are backed by decades of painstaking observations. The CMB approach, meanwhile, is rooted in the fundamental physics of the early universe, yet they stubbornly refuse to reconcile. The discrepancy isn't fading with better data, it's growing. And that suggests something profound. Our understanding of the cosmos might be missing a critical piece. One possibility is that dark energy, the mysterious force speeding up the universe's expansion, isn't constant after all. Maybe it's evolving, growing stronger or weaker over time in ways we haven't accounted for. Others speculate about hidden particles from the early universe, like dark radiation, subtly altering the expansion rate. There's even a radical idea that our corner of the cosmos sits in a peculiar void, a low-density bubble skewing our local measurements. But the most tantalizing and terrifying explanation, that this tension reveals a flaw in our foundational physics. Maybe gravity behaves differently on cosmic scales, or perhaps relativity itself needs tweaking. Einstein once famously added a cosmological constant to his equations to keep the universe static. Could we now need another adjustment to explain why it's expanding faster than expected? The Hubble tension isn't just academic quibbling, it's a crack in the bedrock of cosmology, a sign that the universe still holds cards close to its chest. Solve it, and we might unlock secrets about dark energy, the birth of the cosmos, or even the ultimate fate of everything. Until then, it stands as a humbling reminder, even our best maps of reality are still rough drafts. We've mapped galaxies clustered like cities, traced the cosmic web's luminous threads. But what about the deserts? Imagine a space so empty, so vast, that if our Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s. This isn't science fiction. It's the Boötes void, a spherical abyss spanning 330 million light-years, containing just 60 galaxies where there should be thousands. And it's not alone. Scattered across the cosmos, these voids make up most of the universe's volume, enormous bubbles of near-nothingness that defy everything we know about how matter clumps together. The puzzle isn't just their size, it's their sharp edges. Picture pouring cream into coffee and watching it stop dead, forming a perfect, unmixing boundary. That's how abruptly these voids transition from utter emptiness to the dense galaxy clusters around them. According to simulations, matter should diffuse more gradually, leaving smaller, fuzzier gaps. Yet the voids we observe are like cosmic vacuums, polished clean with unnatural precision. Some researchers propose that dark energy's repulsive force might be actively scooping out these regions, pushing matter toward the web's filaments. Others wonder if primordial sound waves from the Big Bang froze these bubbles into place like echoes fossilized in space-time. But the real shock came when astronomers studied the galaxies trapped inside Boötes. These lonely survivors aren't just rare, they're weird. Many are youthful, blue, and actively birthing stars, unlike the aging red galaxies typically found in undercrowded areas. It's as if the void somehow preserved them in cosmic amber, shielding them from the collisions and gas theft that usually quench star formation. One theory suggests their isolation starves them of new gas, forcing them to recycle what little they have in a slow, sustained burn. What's at stake here isn't just a few oddball galaxies. If voids truly formed differently than our models predict, they could be evidence of exotic physics, perhaps even relics of a pre-Big Bang universe. Or worse, what if they're signs that gravity itself behaves differently in these emptinesses, subtly bending the rules we thought were universal? Every time we stare into one of these voids, it's like the cosmos is staring back, asking a single, haunting question. Are you sure you know how I work? One moment, the cosmos is silent. The next, a burst of radio waves brighter than 1 billion suns erupts across the universe, then vanishes in less time than it takes to blink. These are fast radio bursts, some of the most explosive yet fleeting signals we've ever detected, and we're only just beginning to unravel their secrets. First discovered in 2007, FRBs pack more energy in a millisecond than our Sun emits in 3 days. But here's the kicker: most flash once and disappear forever, while a rare handful repeat unpredictably, like cosmic Morse code from the void. So what could possibly unleash such titanic, yet vanishingly brief, signals? The prime suspect, magnetars. The corpses of dead stars so dense a teaspoon of their material would weigh 1 billion tons, with magnetic fields strong enough to strip the electrons from your atoms at 1,000 kilometers away. Picture one of these monsters having a starquake, its crust cracking under unimaginable pressure, releasing a tsunami of energy that ripples across the universe as an FRB. In 2020, we caught one red-handed, a magnetar in our own galaxy firing off a burst eerily similar to the distant FRBs we've observed. It's the closest thing to a smoking gun we've got. But magnetars might not be the whole story. Some bursts arrive with bizarre properties like FRB 2019-2010-28, which pulses with a 16-day cycle, active for 4 days, silent for 12. Others, like the infamous Lorimer burst, are lone wolves screaming into the dark just once. Then there's the sheer distance problem. Many FRBs originate billions of light years away, meaning whatever's producing them has to be ludicrously powerful to remain visible across such vast stretches of space. Could there be multiple culprits, colliding neutron stars, cosmic strings, hypothetical defects in spacetime itself, or something even stranger? The repeating bursts add another layer of intrigue. If a one-off FRB is a cosmic car backfiring, the repeaters are engines idling, hinting at a process that doesn't destroy its source. Some theories suggest these might be powered by young magnetars still swaddled in debris from their explosive births, their outbursts fueled by falling stellar material. Others propose bizarre celestial lighthouses, beams of radiation sweeping past Earth as their source rotates, flickering in and out of view. And then there's the most tantalizing question of all: could some FRBs be artificial? The pulses are so intense, so tightly concentrated, they resemble the kind of signals we might produce if we aimed a planet-sized transmitter at the stars. While there's zero concrete evidence for alien origins, the mere possibility has astronomers listening closely. After all, if something or someone out there is deliberately blasting these signals across the cosmos, they'd be the perfect interstellar flare, brief, bright, and impossible to ignore. What makes FRBs so electrifying isn't just their mystery, it's their potential as cosmic tools. Because these bursts travel billions of light years, their waves get stretched and scattered by the sparse atoms floating between galaxies. By decoding that distortion, we've begun weighing the universe's missing matter, probing the invisible threads of the cosmic web. It's like using a lightning bolt to illuminate a foggy landscape. Suddenly, we can see the unseen. Yet for every answer they provide, FRBs whisper a dozen new questions. Why do some repeat while others vanish? What cosmic furnaces forge such fleeting fury? And what else might be lurking in the quiet between the bursts? The universe, it seems, still has a few tricks up its sleeve. The universe should be teeming with life. Think about it, with hundreds of billions of galaxies, each containing hundreds of billions of stars, and countless planets in the habitable zones where liquid water could exist, the numbers scream that we shouldn't be alone. And yet, when we listen, the cosmos is silent. No signals, no visits, no evidence of civilizations beyond our own. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One of the most unsettling explanations is the Great Filter, a hypothetical barrier so extreme that it prevents life from progressing to interstellar civilization. The terrifying part, we don't know if we've already passed it or if it's still ahead of us. If the filter is behind us, say, the near-miraculous series of events that led to multicellular life, then we might truly be alone, rare survivors in a cosmic graveyard. But if it's ahead, a looming catastrophe like nuclear war, runaway AI, or environmental collapse, then every technological civilization might hit a wall and vanish before they ever leave their home system. Then there's the dark forest theory, a chilling idea that advanced civilizations stay silent because broadcasting your location is suicidal. Imagine the universe as a forest at night, where every hunter hides, terrified of revealing themselves to predators. Any civilization foolish enough to send signals might attract something far worse, something that eliminates competition before it becomes a threat. If true, our frantic efforts to contact aliens could be the equivalent of shouting in the dark. Others argue the answer is simpler. We're just early. The universe is 13.8 billion years old, but Earth-like planets only started forming in significant numbers around 5 billion years ago. Intelligent life might still be rare, still evolving, leaving us as cosmic pioneers rather than latecomers. Or perhaps spacefaring civilizations exist, but they're so advanced we're like ants trying to comprehend the internet. Their technology, their ways of communicating, we might not even recognize them as artificial. The most haunting possibility, that we're the first, that somewhere in this vast, ancient universe we're the ones who'll light the torch. Or that we're the ones destined to flicker out, another silent warning to whatever comes next. The Fermi Paradox isn't just a question, it's a mirror, forcing us to confront how little we know about our place in the cosmos. And until we find an answer, that silence will keep staring back. In the vast emptiness between planets, where gravity's grip is supposed to be predictable, two tiny spacecraft defied expectations and left scientists scratching their heads for decades. The Pioneer probes, launched in the 1970s to explore the outer solar system, began drifting off course in ways Newton's laws couldn't explain. As they sped toward the distant reaches, something was subtly tugging them backward, an unaccounted-for deceleration so faint it was barely measurable, just a fraction of a nanometer per second squared. But in the precision-driven world of orbital mechanics, even the tiniest discrepancy can hint at something profound. This was the Pioneer Anomaly, a cosmic whisper that seemed to challenge our understanding of physics itself. At first, wild theories flourished. Could it be evidence of invisible dark matter tugging at the probes? Or perhaps a flaw in Einstein's general relativity, manifesting only in the depths of space? The most tantalizing idea, that we'd stumbled upon a new force of nature, one too subtle to detect anywhere but in the lonely trajectories of these distant spacecraft. The anomaly became a rallying cry for theorists, a puzzle that promised, if solved, to crack open new frontiers in physics. But science has a way of humbling grand expectations. Years of meticulous analysis revealed a far more mundane culprit: heat. The probe's plutonium-powered generators were radiating warmth unevenly, creating a faint but constant push against their direction of travel. Imagine drifting in a car with a window slightly open. The subtle pressure of escaping air can nudge you off course over time. That's essentially what was happening to Pioneer, its own warmth acting as a minuscule brake. By 2012, detailed thermal models finally closed the case, proving the anomaly wasn't new physics, just an overlooked engineering quirk. Yet the story doesn't end there. The Pioneer Anomaly's legacy lingers as a cautionary tale and a triumph in equal measure. It reminds us how easily the universe can fool us, how even the tiniest neglected detail can masquerade as a revolution. But it also showcases science at its best, a relentless pursuit of truth where even the most tantalizing mysteries must bow to evidence, and who knows? The next anomaly might not be so easily explained. After all, the cosmos still holds endless secrets, and sometimes the smallest deviations point to the biggest revelations. Empty space isn't really empty. That's one of the strangest truths quantum mechanics has forced us to accept. Even in the deepest void, where not a single atom lingers, the fabric of reality seethes with activity. Particles blinking in and out of existence in a chaotic dance so fleeting we can barely detect it. These are quantum fluctuations, and they might hold the key to one of cosmology's biggest puzzles: why the universe is flying apart faster than anyone predicted. The math behind this is mind-bending. According to Heisenberg's uncertainty principle, you can't ever truly have zero energy in a system. Instead, space is a roiling sea of virtual particles, electron-positron pairs, quarks, even entire atoms constantly forming and annihilating before they can be measured. It's like a cosmic game of whack-a-mole where the moles pop up and vanish in trillionths of a second. But here's where it gets wild. These fleeting particles aren't just mathematical quirks. They generate real, measurable effects. The Casimir effect, for instance, proves this. Place two metal plates incredibly close together in a vacuum, and the plates get pushed toward each other ever so slightly. Why? Because the space between them is too narrow for certain virtual particles to form, creating an imbalance in energy that exerts force. It's proof that nothingness itself has structure and power. Now scale this up to the entire universe. If quantum fluctuations can nudge metal plates, could they also be nudging space-time itself? That's the daring idea some cosmologists are exploring. The vacuum energy created by these particles might be the engine behind dark energy, the mysterious force accelerating cosmic expansion. Picture it like this: every cubic centimeter of space, no matter how empty, is a simmering pot of quantum foam. Multiply that by the staggering volume of the cosmos, and you've got an unimaginable reservoir of energy, pushing galaxies apart like a rising loaf of bread where the dough itself is expanding. But there's a problem. When scientists try to calculate how much energy these quantum fluctuations should contribute, the numbers are catastrophically off. The predicted value is 10 to the power of 120 times larger than what we observe. That's not just a rounding error, it's the worst mismatch in the history of physics. Some call it the cosmological constant problem, and it's so glaring that even Einstein, who first proposed the constant, later dismissed it as his greatest blunder. So where does that leave us? Either we're missing something fundamental about how quantum mechanics interacts with gravity, or there's a cancellation mechanism so precise it zeroes out 120 orders of magnitude without explanation. Some theorists propose that multiple types of virtual particles exist, their energies perfectly counteracting each other in ways we can't yet model. Others suggest that gravity behaves differently at quantum scales, effectively ignoring most of this vacuum energy. The most radical idea that we're seeing evidence of extra dimensions where the true energy of quantum fluctuations leaks into hidden realms we can't perceive. What makes this mystery so urgent is its implications. If quantum vacuum energy is driving cosmic acceleration, it could dictate the universe's ultimate fate, whether we'll end in a big rip, a slow freeze, or something even stranger. And if it's not, then whatever's out there reshaping the cosmos is even more exotic than we dreamed. Either way, the answers lie in the quantum shadows where reality itself flickers in and out of existence. The universe's greatest trick might be hiding its secrets in plain sight, woven into the very fabric of nothingness. Black holes have always been cosmic paradoxes, objects so dense they twist the rules of reality itself. But perhaps their strangest contradiction isn't what they destroy, but what they supposedly erase: information. According to quantum mechanics, information, the fundamental building blocks of what everything is made of, can never truly vanish. It might get scrambled, hidden, or transformed, but it's always preserved. Yet black holes, with their insatiable appetites, seem to break this law. Whatever falls in never comes out, not even the information it carried. This is the black hole information paradox, a puzzle so profound it split physicists into warring camps for decades. The trouble started when Stephen Hawking made a shocking discovery in the 1970s. Black holes, he realized, aren't completely black. Thanks to quantum weirdness, they slowly leak energy particles, escaping their grip in a faint hiss we now call Hawking radiation. Over unimaginable eons, this trickle causes the black hole to evaporate entirely, vanishing as if it never existed. But here's the catch: Hawking radiation is random, carrying no trace of the material the black hole consumed. All the information about what fell in, whether it was a star, a spaceship, or a library of books, appears permanently lost. It's like burning a dictionary and claiming the ashes contain no hint of the words that were printed on its pages. This idea sent shockwaves through physics because quantum mechanics insists information can't be destroyed. At the subatomic level, the universe is a meticulous record keeper. If you knew the exact state of every particle in a system, you could theoretically rewind time and reconstruct its past. But Hawking's calculations suggested black holes shred this cosmic ledger, leaving gaps in the fabric of causality. The implications are staggering. If information can vanish, then the past isn't fixed. Reality itself becomes fuzzy, unpredictable. Not everyone accepted this grim verdict. Some theorists, like Leonard Susskind, argued that Hawking must be wrong. The solution: holography. Imagine a black hole's event horizon as a two-dimensional surface where information gets smeared like ink on a page, preserved in scrambled form. When Hawking radiation escapes, it carries tiny imprints of this data, like a puzzle slowly reassembling itself over eons. In this view, black holes don't destroy information, they just encode it in ways we're only beginning to fathom. Then there's the firewall paradox, a nightmare scenario born from this debate. If information escapes, quantum mechanics demands an invisible wall of searing energy at the event horizon, a brutal cosmic shredder that vaporizes anything falling in. But general relativity says crossing a black hole's threshold should feel like floating into oblivion, no fireworks. Both theories can't be right. The disagreement is so stark it's forced physicists to question whether we've misunderstood spacetime itself. Recent breakthroughs hint at possible resolutions. The discovery of soft hair, a subtle quantum imprint left on a black hole's surface, suggests information might escape via nearly undetectable traces. Others propose that black holes are holograms, with their three-dimensional interiors somehow projected from data stored on their two-dimensional surfaces. It's as if the universe has a backup drive, secretly preserving everything we thought was lost. But the paradox remains unsolved, and that's what makes it electrifying. At its heart, this isn't just about black holes, it's about whether the universe forgets. If information can truly disappear, then reality is less a clockwork mechanism and more a fading dream. If it can't, then somewhere, somehow, even the darkest corners of the cosmos are keeping records we don't yet know how to read. The black hole information paradox isn't just a theoretical squabble, it's a battle for the soul of physics itself. In the cosmic microwave background, that faint afterglow of the Big Bang, there's a patch of sky so peculiarly cold it defies easy explanation. This is the Eridanus supervoid, a region spanning over 1 billion light-years where the temperature of the CMB dips just a fraction lower than its surroundings. At first glance, it might seem like a minor anomaly, a statistical hiccup in an otherwise uniform sea of microwaves, but the scale of this cold spot is what's truly staggering. If it were just a random fluctuation, the odds of something this extreme existing in our observable universe are less than 1 in 50,000. So what's really lurking in this cosmic chill? One theory suggests the void itself is to blame. Supervoid's enormous, underdense regions of space are known to slightly cool light passing through them via a phenomenon called the integrated Sachs-Wolf effect. As photons traverse these vast matter-poor expanses, they lose a tiny amount of energy climbing out of the void's weakened gravitational well, subtly reddening the CMB in that direction. But here's the catch: the Eridanus supervoid, while massive, isn't nearly empty enough to account for the temperature drop we observe. It's like finding a freezer in the desert. Something else must be amplifying the effect. That's where things get speculative. Some cosmologists propose this void might be the imprint of a cosmic defect, a relic from the universe's earliest moments. Picture spacetime as a frozen lake. If cracks formed as it cooled, they could have left behind structures that subtly warp reality itself. Others take it even further, suggesting the cold spot could be evidence of a collision with another universe, a bubble from the multiverse brushing against our own and leaving a bruise in the CMB. It's not as far-fetched as it sounds. Inflation theory, which describes the universe's explosive early growth, naturally predicts the existence of other bubble universes. If one nudged ours, the energy released might have carved out this void and chilled the light within it. Yet not everyone's convinced. Skeptics argue the cold spot might just be an artifact of how we process CMB data, a trick of the eye magnified by the human tendency to find patterns in randomness. After all, if you stare at static long enough, you'll start seeing shapes. Alternative models suggest it could be the result of several smaller voids aligned along our line of sight, their combined effect mimicking a single colossal structure. The Planck satellite's high-resolution scans have added fuel to the debate. While they confirm the cold spot's existence, they also reveal smaller-scale fluctuations that muddy the waters. What makes this mystery so compelling isn't just the science, it's the philosophical stakes. If the Eridanus supervoid is a window into the multiverse, it would be the first tangible evidence that our cosmos is just one among countless others. But if it's a fluke, it's a reminder of how even the most precise observations can lead us down rabbit holes. For now, the cold spot remains an enigma, a cosmic Rorschach test revealing as much about our theories as it does about the universe itself. And until we crack its code, it stands as one of the quietest and most profound puzzles in modern cosmology. We like to think of our place in the universe as ordinary, just another spiral galaxy among billions, drifting through the cosmic web like a leaf on a river. But what if we're actually floating in a cosmic desert, a vast bubble of emptiness that's skewing how we see everything beyond it? Welcome to the KBC Void, a controversial structure that might just rewrite our understanding of the local universe and our own backyard. Named after astronomers Keenan, Barger, and Cowie, who first proposed its existence in 2013, this hypothetical void spans over 2 billion light-years, with the Milky Way sitting uncomfortably close to its center. If real, it would dwarf every other known void in the observable universe, a staggering expanse of underdense space where galaxies are fewer and farther between. The implications, our measurements of cosmic expansion, those critical calculations fueling the Hubble tension, might be hopelessly biased. After all, if you're standing in a valley, the mountains around you will look taller than they really are. Here's how it works. In an underdense region like the KBC void, gravity's pull is weaker, allowing space to expand faster locally. Light from distant supernova, used to measure cosmic expansion, would subtly brighten as it exits this void, mimicking the effects of accelerated expansion we attribute to dark energy. It's like trying to gauge the speed of a river while drifting in a whirlpool. Your measurements won't reflect the true current. This could explain why some local measurements of the Hubble constant clash with those derived from the cosmic microwave background. The discrepancy might not be a flaw in our physics, but a quirk of our unfortunate cosmic address. Not everyone's convinced. Critics argue that a void this large violates the cosmological principle, the idea that, on grand scales, the universe should look roughly the same everywhere. Finding such a colossal anomaly so close to home feels statistically improbable, like winning the lottery and then discovering the ticket in your own pocket. Detailed galaxy surveys have also failed to definitively confirm the void's existence. Some studies even suggest the apparent underdensity might just be a trick of perspective, galaxies hiding behind dust or clustering in ways we haven't fully mapped. Yet the KBC void's defenders counter with an even wilder idea. What if we're not special at all? Simulations suggest giant voids could form naturally, like froth in a boiling pot, with some regions inevitably ending up emptier than others. If that's true, our Milky Way might just be an unlucky traveler, stuck in one of the universe's lonelier neighborhoods. And if we ever confirm this void's existence, it would force us to recalibrate our cosmic yardsticks, accepting that the universe's expansion isn't just speeding up, but doing so unevenly in ways we're only beginning to grasp. The most tantalizing question isn't whether the void exists, it's what else we might be missing. If our local patch of cosmos is this peculiar, how many other anomalies are lurking in the data, quietly distorting our view of reality? The KBC void isn't just a curiosity. It's a humbling reminder that sometimes to see the universe clearly, you first have to step out of your own shadow. Is the universe infinite, stretching endlessly in all directions, or does it curve back on itself like the surface of an impossibly large balloon? The shape of the cosmos isn't just a philosophical question, it's a puzzle written in the fabric of space-time itself, and the answer might rewrite everything we know about reality. For centuries, we've assumed space is flat, obeying the rules of Euclidean geometry we learned in school. But what if that's just an illusion, a local quirk masking a far stranger truth? The key to this mystery lies in the cosmic microwave background, that ancient light from the dawn of time. When scientists mapped its faint whispers, they were searching for subtle distortions, hints that parallel lines might eventually converge or diverge over cosmic distances, revealing whether we live in a closed, open, or flat universe. A closed universe would curve positively, like the surface of a sphere, where traveling far enough in one direction would theoretically bring you back where you started. An open universe would curve negatively, resembling an infinite saddle shape, while a flat universe would expand forever without bending, the shocking result. Within a razor-thin margin of error, the data suggests the universe is flat. But here's the catch: flat on observable scales doesn't necessarily mean infinite. Imagine you're an ant crawling on a soccer ball. If the ball were gargantuan, say, the size of Earth, its curvature would be so slight that your tiny patch of surface would feel perfectly flat. The universe could be playing the same trick on us. Some theories propose it's actually a hypersphere, so vast that its curvature is undetectable within the limits of what we can see. If that's true, the cosmos might be finite but unbounded, like a cosmic Möbius strip with no edges yet no true infinity. But the plot thickens. Topology, the study of shapes and their properties, suggests even wilder possibilities. The universe could be torus-shaped, a giant donut where traveling far enough in one direction would loop you around to the other side. Or it might be multiply connected like a hall of mirrors with identical regions repeating in ghostly patterns across space. The most mind-bending idea, a Klein bottle universe where space twists in on itself in higher dimensions, turning inside out without crossing any boundaries. How could we ever test these ideas? One clue might lie in the cosmic microwave background. If the universe has a repeating structure, we'd expect to see matching patterns in the CMB, like celestial fingerprints reappearing at regular intervals. Another approach involves hunting for ghost galaxies, pairs of distant objects that are actually the same galaxy seen from different angles due to the universe's topology folding light back on itself. So far, no definitive matches have been found, but the search continues. The stakes couldn't be higher. If the universe is finite, it would mean everything we see, every star, every galaxy is just a tiny fraction of a grander structure, like a single tile in an endless mosaic. If it's infinite, the implications are even more staggering. An inexhaustible expanse where every possible configuration of matter must repeat, rendering copies of you, me, and every conceivable world somewhere in the void. Either way, the universe's true shape remains one of its most profound secrets, hiding in plain sight, waiting for us to decipher its geometry. And when we do, we won't just be mapping space, we'll be uncovering the very blueprint of reality. The Big Bang is often presented as the ultimate beginning, a singular moment when time, space, and matter erupted into existence. But what if the truth is far stranger? What if the universe didn't actually begin at all? The closer we look at that fiery instant, the more the story unravels. At the heart of the Big Bang lies a singularity, a point of infinite density where the laws of physics as we know them break down completely. Gravity becomes so intense that spacetime itself curves beyond recognition, and our equations spit out nonsensical infinities. It's like asking what's north of the North Pole. The question might not even make sense. But scientists refuse to accept "we don't know" as the final answer. One daring idea: the universe cycles. In these models, the Big Bang wasn't a true beginning but a rebirth, a cosmic phoenix rising from the ashes of a previous collapse. Picture two sheets of spacetime colliding in higher dimensions, igniting a new expansion. Or imagine a universe that expands until dark energy tears it apart, only for quantum fluctuations to spark another bang in the void. These cyclic cosmologies suggest an eternal rhythm with no start and no end, just an endless dance of creation and destruction. Then there's the multiverse angle. If our universe is just one bubble in an infinite froth of others, each with its own laws of physics, then the Big Bang might have been a local event, a tiny pocket of stability in a seething quantum foam. Some theories propose that universes spawn from black holes in other universes, meaning our entire cosmos could be the offspring of a singularity in some distant alien reality. It's a dizzying thought. Every black hole in our universe might contain an infant cosmos of its own, branching endlessly like a fractal. But the most radical rethink comes from quantum gravity. Theories like loop quantum gravity suggest the singularity never happened, that spacetime isn't infinitely divisible but made of tiny, indivisible grains. At the Big Bang, these grains would resist further compression, causing the universe to bounce instead of collapsing into infinity. Imagine squeezing a spring to its limit. Instead of breaking, it recoils. If this is true, the Big Bang might have been the big bounce, with traces of the previous universe lingering in the cosmic microwave background like echoes in a cave. The truth is, we're peering into the ultimate darkness. Without a theory that unites quantum mechanics and gravity, the Big Bang's singularity remains a locked door. But behind it could lie answers to existence itself, whether we're one turn in an endless cycle, a branch on an infinite tree, or something beyond our wildest imagination. Every time we think we've grasped the beginning, the universe whispers, "Look deeper. Here's a cosmic recipe that's gone horribly wrong." Take one rapidly expanding universe fresh from the Big Bang, sprinkle in protons and neutrons, cook at 1,000,000,000,000 degrees, and out should pour the lightest elements in precise quantities. Hydrogen, helium, and a pinch of lithium. These were the universe's first atoms forged in the fires of creation. The calculations are exquisite, matching observed helium and deuterium levels almost perfectly. But lithium, that's where the math falls apart. According to every textbook, there should be about 3 times more lithium-7 in the cosmos than what we actually find. And lithium-6, which shouldn't even exist in measurable amounts from the Big Bang alone, somehow it's there. This glaring mismatch is the lithium problem, and it's been haunting astrophysicists for decades. Let's rewind to the first few minutes after the Big Bang, when the entire universe was a nuclear fusion reactor. As space expanded and cooled, protons and neutrons began combining into heavier nuclei, a process called Big Bang nucleosynthesis. The amounts produced depend on factors like density, temperature, and the expansion rate, all pinned down by the laws of physics. For helium-4 and deuterium, the predictions align neatly with what we see in ancient stars and gas clouds. But lithium is the stubborn outlier. It's as if the universe followed the recipe perfectly, then deliberately left out an ingredient, one possible explanation. Our understanding of those first nuclear reactions might be incomplete. The rates at which protons and neutrons fused into lithium could have been miscalculated, perhaps due to undiscovered quantum effects or errors in how we model the chaotic conditions of the early universe. Some theorists suggest exotic particles might have been involved, like certain types of dark matter that could have altered the nuclear balance. Others propose that lithium gets destroyed over time, maybe by settling into stars' cores where it's burned away, or by interacting with cosmic rays that break it apart. But here's the twist: the problem gets even weirder when we look at the oldest stars in our galaxy. These ancient suns, formed from nearly pristine Big Bang material, should reflect that primordial lithium abundance. Instead, they show even less lithium than expected, as if something had been scrubbing it from the cosmos for billions of years. And then there's lithium-6, the isotope that Big Bang nucleosynthesis shouldn't have made in detectable quantities, yet it's there, staring back at us from stellar spectra. Did some unknown astrophysical process create it later, or does its presence hint at entirely new physics operating in the universe's first moments? The most radical solutions venture into uncharted territory. Could decaying dark matter particles have soaked up extra neutrons, skewing the nuclear balance? Might there have been pockets of uneven temperature in the early universe, creating local variations in element production? Almost intriguingly, could this mismatch be a clue that the Big Bang wasn't as uniform as we think, that some asymmetry or instability left its mark in these elemental discrepancies? For now, the lithium problem remains one of cosmology's quiet embarrassments, a tiny anomaly with potentially massive implications. Every unresolved photon, every stubborn isotope is a whisper from the dawn of time, hinting that our picture of the universe's birth is still missing something fundamental. And until we solve it, we can't be entirely sure we've cracked the first chapter of cosmic history. At the outer edges of our solar system, something massive is pulling at the cosmos, something we've never seen. Distant icy objects far beyond Neptune are clustering in orbits that shouldn't make sense, their paths tilted in ways that suggest an unseen hand is guiding them. Astronomers call this phantom influence planet 9 a hypothetical world up to 10 times heavier than Earth, lurking in the frozen darkness. But if it's really out there, why can't we spot it? And what does its existence or absence say about the untold stories of our cosmic neighborhood? The clues began stacking up in 2014 when astronomers Chad Trujillo and Scott Shepard noticed a bizarre pattern. Several trans-Neptunian objects, icy bodies like Sedna and Biden, shared oddly similar, highly elongated orbits, tilted at nearly identical angles. Statistically, the odds of this happening by chance were less than 1 in 1,000. Then came the kicker. Simulations showed that a massive, distant planet could be herding these objects into their strange configurations, like an invisible shepherd guiding its flock. Further studies revealed even more eerie alignments, with some objects' orbits pointing in the same general direction, as if something massive were tugging them into place. But hunting this ghost planet is like searching for a black cat in a pitch-black room while wearing sunglasses. Planet 9, if it exists, could orbit up to 20 times farther from the Sun than Neptune, making it incredibly faint. Its year might last up to 20,000 Earth years, meaning it moves agonizingly slowly across the sky. And because we don't know exactly where to look, telescopes have to scan vast swaths of space, hoping to catch a single pixel shifting against the stars. The best guess, Planet 9 could be a super-Earth or a mini-Neptune, a world unlike anything in our inner solar system. Some theories suggest it was flung outward during the solar system's violent youth, while others propose it might be a rogue planet captured by the Sun's gravity long ago. There's even a fringe idea that it's not a planet at all, but a primordial black hole, no larger than a grapefruit yet massive enough to explain the gravitational anomalies. Skeptics argue the evidence could be a fluke, a case of observational bias where we're only seeing the objects that fit the pattern while missing those that don't. Others suggest a passing star billions of years ago might have yanked these icy bodies into their strange orbits without leaving a planet behind. But the more data we collect, the harder it becomes to dismiss the idea entirely. New surveys like the Vera Rubin Observatory's upcoming sky scans could finally settle the debate, either spotting Planet 9 or forcing us to rethink the clues entirely. What makes this search so thrilling isn't just the potential discovery, it's the reminder that our solar system might still hold colossal secrets. If Planet 9 is real, it would rewrite the story of how planetary systems form and evolve. And if it's not, then something even stranger is out there, warping the motions of distant worlds without leaving a trace. Either way, the hunt continues, a cosmic game of hide and seek at the edge of everything we know. On August 15, 1977, a radio telescope in Ohio picked up something impossible to ignore. A signal so strong, so obviously artificial seeming, that the astronomer who discovered it circled the printout and scribbled, "Wow." In the margin, that single word gave the signal its name, and for decades, it's been the closest thing we've had to proof that we might not be alone in the universe. The numbers tell the story. The WOW signal blasted in at 1420 MHz, a frequency smack in the middle of what scientists call the water hole, a quiet band of the radio spectrum where hydrogen and hydroxyl molecules emit natural signals, making it a prime channel for interstellar communication. It lasted 72 seconds, the exact duration the telescope could focus on a single point in the sky, and it was 30 times louder than the cosmic background noise. Most telling of all, the signal was narrowband, meaning it was concentrated on one specific frequency, something natural cosmic phenomena almost never do. Lightning, pulsars, quasars, they all broadcast across a wide range of frequencies. This was a laser-sharp scream in the static. Then, just as suddenly as it appeared, it vanished. Despite dozens of attempts to find it again, the WOW signal never repeated. That's what makes it so maddening. If it was a beacon from another civilization, why did it flicker on and off like a cosmic lighthouse with a burned-out bulb? In 2017, a new theory emerged, one that seemed at first to solve the mystery. Astronomer Antonio Paris proposed the signal might have come from a passing comet. Specifically, two comets 266P/Christensen and 335P/Gibbs were in roughly the same patch of sky where the WOW signal originated. Comets surrounded by clouds of hydrogen gas could theoretically emit radio waves at the right frequency. Case closed, not quite. The comet explanation has more holes than a spaceship after a meteor shower. For starters, those comets weren't discovered until years after the WOW signal was detected, meaning no one knew to look for them in 1977. More critically, comets don't emit narrowband signals. Their hydrogen clouds produce broad, messy radio noise, nothing like the precise, focused burst that stunned astronomers that summer night. Even if a comet was responsible, why hasn't a similar signal been detected since? The skies are full of comets, yet the WOW signal remains one of a kind. Which leaves us back where we started, with a signal that fits every criterion we'd expect from an intelligent transmission, yet can't be proven or replicated. It's the ultimate cosmic tease, a single, brilliant flash in the dark that might be the closest we've ever come to hearing from another civilization, or just a freakish natural phenomenon we don't yet understand. The real sting we may never know. The WOW signal is like a message in a bottle washed ashore just once, leaving us to wonder who wrote it, or if we just imagined the whole thing. Until another signal like it comes along, it remains the universe's most tantalizing unanswered call. Every galaxy we've ever studied floats in a vast, invisible halo of dark matter until this one. Meet NGC 1052DF2, a ghostly galaxy that defies everything we thought we knew about how galaxies form. This cosmic oddball, discovered in 2018, is so lacking in dark matter that it shouldn't exist. It's like finding a car speeding down the highway with no engine. Physics says it's impossible, yet there it is, cruising along like nothing's wrong. Galaxies are supposed to be glued together by dark matter's gravitational pull. Without it, the outer stars should fling themselves into the void, unable to resist the centrifugal force of the galaxy's spin. Yet NGC 1052DF2's stars orbit at a leisurely pace, perfectly content in their dark matter-free existence. At first, astronomers doubted the measurements. Maybe the galaxy was closer than estimated, making it appear dimmer and less massive. But follow-up observations with Hubble and the Keck Observatory confirmed the unthinkable. This galaxy's mass comes almost entirely from visible stars and gas, with almost no dark matter at all. The discovery sent shockwaves through astrophysics. Dark matter isn't just a minor ingredient in galaxies, it's the cosmic scaffolding that holds them together. Current models suggest galaxies form when dark matter clumps into halos, attracting gas and dust that eventually ignite into stars. Without dark matter, how did NGC 1052DF2 even assemble itself? One theory proposes it might be a failed galaxy, a rare case where gas somehow collapsed directly into stars without a dark matter backbone. Another idea is more dramatic. Perhaps it was once a normal galaxy until a violent encounter with a neighboring galaxy stripped away its dark matter like a cosmic thief in the night. The plot thickens when you consider this galaxy's surroundings. It lives near a massive elliptical galaxy called NGC 1052, a gravitational bully that could have played the role of that thief. Simulations show that if NGC 1052DF2 passed too close, tidal forces might have ripped away its dark matter while leaving the stars relatively untouched. It's like plucking the bones from a body but leaving the skin intact, a gruesome cosmic surgery. But not everyone's convinced. Some researchers argue that our methods for measuring dark matter could be flawed, especially in these ultra-diffuse galaxies where stars are spread incredibly thin. Others suggest that dark matter might still be there, just hiding in an unexpected form, perhaps clumped in a way our current tools can't detect. The most tantalizing possibility. That NGC 1052DF2 is a signpost pointing to a whole new class of galaxies, ones that form through processes we haven't even dreamed of yet. What makes this mystery so electrifying isn't just the galaxy itself, it's what it represents. If dark matter isn't as universal as we thought, it could mean our understanding of galaxy formation is missing a crucial chapter. Or worse, what if dark matter isn't the only way to build a universe? NGC 1052DF2 is more than an anomaly. It's a challenge, a cosmic riddle scribbled in starlight, daring us to rethink the rules we thought were set in stone. And until we solve it, every galaxy we study will come with a silent question. Are we seeing the whole picture, or just the parts the universe wants us to see? The cosmic microwave background is often called the universe's baby picture, a snapshot of the cosmos just 380,000 years after the Big Bang. But zoom in, and this baby picture starts to look odd. We've already discussed the axis of evil and the Eridanus cold spot, but those are just the tip of the iceberg. The CMB is riddled with anomalies, tiny wrinkles in space-time that refuse to fit our tidy theories, and some of them might be whispering secrets about forces we've yet to imagine. Take the so-called dark flow, a bizarre, unexplained motion where entire galaxy clusters appear to be streaming toward a single point in space like leaves caught in a cosmic wind. This isn't just drift. Measurements from the Wilkinson microwave anisotropy probe and later the Planck satellite revealed that hundreds of galaxy clusters are all moving in the same direction at speeds exceeding 1 million miles per hour. The kicker, there's nothing massive enough in that direction to explain the pull. No supercluster, no concentration of dark matter, just empty space. It's as if something beyond the edge of our observable universe is yanking on the cosmic fabric, something so enormous it warps gravity across unfathomable distances. One radical explanation, another universe, part of a vast multiverse, might be tugging on ours through some higher dimensional leak. Or perhaps space-time itself has large-scale structures we don't yet understand, wrinkles left over from the Big Bang that funnel matter like currents in an invisible river. Then there's the hemispheric asymmetry, another crack in the cosmos's otherwise pristine facade. The CMB should look roughly the same in all directions, a uniform sea of microwaves. But when scientists split the sky into hemispheres, they found one side is subtly hotter than the other, as if the universe were lopsided at birth. The difference is tiny, just a fraction of a degree, but in a realm where precision is everything, it's like finding a fingerprint on a supposedly untouched crime scene. One theory suggests this could be evidence of an ancient collision with another universe during inflation. A primordial crash that left one side of our cosmos slightly bruised. Others propose that the asymmetry stems from an uneven expansion in the universe's earliest moments, a hiccup in spacetime's growth spurt that froze into the CMB's structure. But here's what makes these anomalies so unnerving. They challenge the cosmological principle, the bedrock idea that the universe is homogeneous and isotropic, basically, that it looks the same everywhere when viewed on large enough scales. If these irregularities are real and not just statistical flukes, they could mean our universe isn't as uniform as we thought. Some regions might be fundamentally different from others, governed by slightly altered physics or shaped by forces we've yet to discover. It's like realizing the walls of your house aren't straight, that the foundation itself is warped in ways you never noticed. And then there's the great silence, an eerie absence of expected large-scale fluctuations. At certain angular scales, the CMB's temperature variations are mysteriously muted, as if someone turned down the volume on the universe's background static. This missing power suggests that either our models of the early universe are missing a key ingredient, or something suppressed density fluctuations on those scales during inflation. Maybe an unknown field interacted with the inflaton, the particle responsible for cosmic expansion, leaving behind this telltale hush. Each of these anomalies could be a fluke, a trick of the data. But together, they form a pattern too compelling to ignore. They're like breadcrumbs scattered across the cosmos, leading us toward something we can't quite see yet. Whether they point to new physics, hidden dimensions, or even other universes, one thing's certain: the cosmic microwave background isn't just a relic of the past. It's a living puzzle, a map with X's marking spots we've only begun to dig, and the deeper we look, the stranger the treasure gets. Imagine a black hole so massive, so powerful, that it tears itself free from the very galaxy that birthed it, hurtling through the cosmos at millions of miles per hour, untethered and unstoppable. These are hypervelocity black holes, cosmic outcasts flung into the void by forces so violent they defy comprehension. And their existence reveals a hidden truth. Galaxies aren't just serene islands of stars. They're battlegrounds where collisions of unimaginable scale can catapult the universe's most terrifying objects into the abyss. The story begins when two galaxies merge, their central supermassive black holes spiraling toward each other in a deadly dance. As they orbit closer, they emit ripples in space-time gravitational waves that carry away energy, tightening their orbit until the final cataclysmic collision. But here's where physics throws a curveball. If the merger isn't perfectly symmetrical, the newborn black hole can recoil from the gravitational waves like a gun firing backward, launching itself at speeds up to 5,000 kilometers per second. That's fast enough to cross the distance from Earth to the Moon in under 2 minutes. We've actually caught these fugitives in the act. In 2017, astronomers spotted a quasar, a blazing beacon of light from a black hole's accretion disk 3 billion light-years away, streaking through its galaxy at roughly 8 million kilometers per hour. The kicker, the black hole wasn't alone. It left a trail of young stars in its wake, cosmic breadcrumbs hinting at its violent exit. As the black hole plowed through gas clouds, it likely triggered star formation in its chaotic wake, like a rogue bulldozer igniting fireworks as it crashes through a factory. But the real shock came when researchers realized some hypervelocity black holes might be completely invisible. Without gas to feed on, these dark fugitives would leave no glowing accretion disk, no quasar to betray their presence. They'd roam the cosmos undetected, their presence only revealed by the subtle warping of starlight as they pass, a ghostly fingerprint on the sky. Some theorists even suggest our own Milky Way could host one of these lone wanderers, a silent shadow drifting unnoticed through our galactic backyard. What makes these runaway black holes so fascinating isn't just their speed, it's what they teach us about the chaos of galactic evolution. Their trajectories are cosmic records of ancient collisions, clues to how galaxies grow by devouring each other. By tracing their paths backward, we might reconstruct violent encounters that happened billions of years ago, like detectives piecing together a crime scene from a single bullet's trajectory. And then there's the existential question, where do they go? A black hole ejected from its galaxy is condemned to an eternity in the void, a nomad with no home. Some might eventually slow down, captured by another galaxy's gravity to begin the cycle anew. Others could drift forever, their immense gravity too weak to attract matter in the near-empty intergalactic darkness. It's a haunting thought that the universe's most destructive forces might also be its loneliest travelers, doomed to wander the endless night. Yet in their solitude, these rogue black holes might seed future mysteries. If one passed through a cloud of cold gas, could it ignite a new quasar, lighting up the cosmic darkness like a match struck in a cave? Or could they explain weird, isolated flares, flashes of energy with no visible source, as if space itself were screaming in the dark? Every hypervelocity black hole is a reminder that the universe is far from static, that even the mightiest objects are at the mercy of gravity's whims. And somewhere out there, in the black between galaxies, countless more are waiting to be found, each one a bullet fired from the chaos of creation itself. Right now, the universe is expanding, that much we know. But where is it all headed? Will galaxies drift apart forever, fading into infinite darkness, or does gravity still hold a cosmic trump card, one that could reverse the expansion and pull everything back together in a fiery collapse? The universe's ultimate fate hinges on a tug of war between two titanic forces: dark energy, which is speeding up the expansion, and gravity, which tries to rein it all in. And depending on who wins, the finale could be a slow fade, a violent tear, or a dramatic rebirth. First, consider the Big Freeze, also called heat death. In this scenario, dark energy keeps accelerating the expansion indefinitely, pushing galaxies apart until the space between them becomes an impassable gulf. Star formation sputters out as galaxies exhaust their gas. One by one, the lights go dark, and black holes evaporate over eons via Hawking radiation. Eventually, even protons decay, leaving behind a sea of subatomic particles so spread out they'll never interact again. The universe doesn't so much end as it does fizzle, like an ember cooling to absolute zero. Right now, this is the leading theory, backed by observations of dark energy's relentless push. But it's not the only possibility. Then there's the Big Rip, a far more violent finale. If dark energy isn't just constant but grows stronger over time, it could eventually overpower even the forces binding atoms together. Picture this: first, galaxies are torn apart, then solar systems, then planets, until finally, in the last moments, even atomic nuclei are shredded into quarks. The universe would end not with a whimper but a scream. Some models suggest this could happen in as little as 22 billion years, a blink on cosmic timescales. The key factor: whether dark energy is phantom energy, a hypothetical form that intensifies as space expands. Current data isn't conclusive, but the mere possibility keeps cosmologists awake at night. But what if gravity gets the last laugh? Enter the Big Crunch, a dramatic reversal where expansion slows, halts, and then collapses back in on itself. Galaxies would rush toward each other, temperatures skyrocket, and eventually the entire universe condenses back into a singularity, perhaps birthing a new Big Bang in an endless cycle. This was once the dominant theory, but it's fallen out of favor since dark energy's discovery. Still, some researchers speculate that dark energy might decay over time, weakening just enough for gravity to regain control. And then there's the wild card: vacuum decay. If our universe isn't in the lowest possible energy state, a quantum fluctuation could trigger a bubble of true vacuum to form, expanding at light speed and rewriting the laws of physics as it goes. One moment, reality as we know it exists; the next, it's overwritten by something entirely alien. It's unlikely, but not impossible. What's fascinating isn't just the scenarios, it's how little we truly know. The universe's fate hinges on the nature of dark energy, and right now, dark energy is a mystery wrapped in an enigma. Is it constant, evolving, or something we haven't even conceived of yet? Every new observation, from distant supernova to the cosmic microwave background, is a clue in the ultimate detective story. And the ending, well, that's still being written. The idea that our universe might be just one of many, a single page in an infinite cosmic library, isn't science fiction anymore. It's a serious scientific hypothesis, one that comes in flavors so varied they'd put an ice cream shop to shame. From parallel realities where every possible outcome plays out to bubble universes with entirely different laws of physics, the multiverse isn't a single theory, it's a spectrum of possibilities, each stranger than the last. Start with level I, the simplest version. Imagine the universe is infinite, stretching endlessly in all directions. If that's true, then every possible arrangement of matter must repeat somewhere out there. There's a copy of you reading this script right now, but with a blue shirt instead of red. Another where dinosaurs never went extinct. Another where your coffee is just slightly colder. In this infinite sea, every event that could happen does happen somewhere. The kicker: this isn't speculation, it's a direct consequence of cosmological inflation, the same theory that explains the Big Bang's aftermath. If space expanded exponentially in those first moments, as evidence suggests, then an infinite universe isn't just possible, it's likely. Then there's level Roman 2, where things get spicy. Inflation might not have stopped uniformly. Picture a pot of boiling water, bubbles form, expand, and collide. Now replace water with space-time. some regions stop inflating, becoming stable universes like ours, while others keep stretching forever, spawning new bubbles with every quantum flicker. Each bubble could have different fundamental constants: a universe where gravity is stronger, where atoms never form, or where time runs backward. This isn't just theoretical. The math of inflation practically demands these bubbles exist. The problem, we'll never see them. The space between bubbles expands faster than light, placing them forever beyond our cosmic horizon. Level Roman 3 takes quantum mechanics and cranks it to 11. Every time a particle exists in multiple states, like Schrödinger's famous dead and alive cat, the universe splits. Not metaphorically, literally. In one branch the cat lives, in another it doesn't. This is the many worlds interpretation, where every quantum decision spawns new timelines. Unlike level I, these universes aren't far away in space. They're right here, stacked like layers in a phantom dimension. The eerie part: this isn't wild conjecture. It's one of the few ways to explain quantum weirdness without invoking conscious observers collapsing reality. But testing it, that's the rub. By definition, these branches don't interact. You can't peek into a universe where you married your high school sweetheart or invented time travel. Then there's level Roman 4, the wild card, proposed by physicist Max Tegmark. This one says every mathematically possible universe exists. Not just variations on our physics, but realities where 2 + 2 = 5, where dimensions curl in on themselves, where causality is optional. It's the ultimate democracy of existence. If the equations work, the universe is real. No need for fine-tuning or luck. Every option is on the table. The catch: it's untouchable by science. When literally anything is possible, how do you test it? So, are these multiverses science or philosophy? Some, like level I, are nearly inevitable if we accept inflation. Others, like level Roman 3, solve genuine quantum puzzles. But until we find hard evidence, cosmic bruises from colliding bubble universes, anomalous imprints in the SIMB hinting at other timelines, they'll remain tantalizing maybes. What's clear is this: the multiverse isn't a cop-out, it's a frontier, and whether it's real or not, the mere possibility forces us to ask the deepest question of all. In a cosmos this vast, what does alone even mean? What if everything around us, the stars, the planets, even the air you're breathing right now, isn't real? Not in the way we think, anyway. What if the universe, with all its galaxies and black holes and mysteries, is nothing more than an unimaginably advanced simulation running on some cosmic computer? This isn't just the plot of a sci-fi movie. It's a serious hypothesis called the simulation argument, and it's gained traction among physicists, philosophers, and even Silicon Valley tech giants over the past 2 decades. The idea is as unsettling as it is fascinating. If a civilization could one day create simulations indistinguishable from reality, the odds suggest we're more likely to be inside one than not. Let's start with the math. In 2003, philosopher Nick Bostrom laid out a disconcerting trilemma. 1. Nearly all civilizations at our level of technological development go extinct before achieving the ability to run ancestor simulations, high-resolution virtual worlds populated by conscious beings. 2. If they do survive, they almost never choose to run such simulations, perhaps for ethical reasons. Or 3. We are almost certainly living in a simulation. Bostrom's argument hinges on probability. If even a tiny fraction of advanced civilizations run simulations, the number of simulated minds would dwarf the number of real ones. Statistically, you're more likely to be one of the copies, but this isn't just philosophical sleight of hand. There are hints, tiny, unsettling anomalies that could point to a simulated universe. Take quantum mechanics, for instance. At the smallest scales, particles don't behave like smooth, continuous objects. Instead, they jump between discrete energy levels as if the universe has a frame rate. This quantization of properties like energy and spin looks eerily like pixels in a video game, a cosmic resolution limit. Then there's the speed of light. Why is there a hard-coded maximum speed for information? Could it be the processing power of the simulation's hardware struggling to keep up? Even the fabric of spacetime itself might be giving us clues. Some theories suggest spacetime could be fundamentally pixelated at the Planck scale, distances so small that trying to measure anything shorter would require so much energy it would collapse into a black hole. It's as if the universe is rendering reality in tiny, indivisible chunks, just like a computer approximates curves with polygons. And what about glitches? Some physicists have speculated that high-energy cosmic rays, which inexplicably break the expected energy limits, could be artifacts of the simulation's code, like rounding errors in a colossal calculation. Now, here's the real kicker. If we are in a simulation, the creators might have left Easter eggs. Mathematician Edward Frenkel once suggested that advanced simulators could encode messages in the very structure of reality, hidden in the digits of irrational numbers like pi, or woven into the constants of nature. Others propose that quantum entanglement, where particles instantly influence each other across vast distances, is a shortcut the simulation uses to save processing power, like a video game only rendering what the player can see. Of course, not everyone's convinced. Critics argue that simulating every particle in a universe, let alone conscious minds, would require energy and computational resources beyond comprehension. But what if the simulation isn't rendering everything at once? It could be generating reality only when observed, like a video game loading assets as you explore. Sound familiar? That's essentially the Copenhagen interpretation of quantum mechanics, where particles exist in a haze of probabilities until measured. The simulation argument forces us to confront profound questions. If this is a simulation, is there any way to hack it? Could we communicate with the simulators or even escape? And if we're not real in the traditional sense, does that make our experiences any less meaningful? Some researchers have proposed experiments to test the hypothesis, like looking for pixelation in high-energy physics or exploiting quantum quirks to force a buffer overflow in the simulation's code. But perhaps the most haunting implication is this: even if we're simulations, our creators might be simulations too, nested in an infinite regression of realities. After all, if they can simulate us, what's stopping their universe from being someone else's simulation? It's turtles all the way down, a cosmic hall of mirrors where the line between real and artificial blurs into oblivion. Whether it's true or not, the simulation argument does one thing brilliantly. It holds up a mirror to our place in the cosmos and asks with a sly smile, "How sure are you?" We've journeyed through the cosmos' greatest enigmas: dark energy's relentless push, dark matter's ghostly grip, the eerie silence of Fermi's paradox, and yet with every answer, a dozen new questions emerge. Think about it, we're surrounded by mysteries so profound they defy the very laws we thought governed reality. Black holes that erase information, voids so vast they warp our view of the universe, cosmic anomalies that hint at realms beyond our own. Each discovery peels back another layer, revealing just how much we still don't understand. Take dark energy, for example. It makes up nearly 70% of the universe, yet we have no idea what it actually is. It's like trying to describe an invisible elephant in the room. We can see the furniture being shoved around, but the elephant remains a shadow and dark matter. It outweighs normal matter 5 to 1, yet it slips through our detectors like a whisper in a hurricane. After decades of searching, we're still grasping at cosmic smoke. Then there's the unsettling truth that half the ordinary matter in the universe is simply missing. Not exotic particles, not some theoretical construct, just the stuff you, me, and the stars are made of. It's like misplacing the keys to reality itself. And let's not forget the cosmic microwave backgrounds, cold spots and alignments, flukes so statistically improbable they've left scientists questioning whether we've misread the universe's blueprints entirely. The most humbling realization, this is just the beginning. For every mystery we've touched on, Planet Nine's gravitational whispers, the WOW signal's lonely cry, the simulation hypothesis existential twist, countless others lurk in the shadows. What sparked the Big Bang? Are we alone in the cosmos? Is reality itself a fractal of multiverses, each with its own rules? The universe isn't just stranger than we imagine, it's stranger than we can imagine. So here's the invitation: keep looking up, stay curious, because the greatest stories aren't the ones we've solved, they're the ones still waiting to be told. If this journey through the unknown has sparked even a fraction of the wonder we feel making it, then the cosmos has done its job, and who knows, the next cosmic revelation might be just around the corner. Until then, the universe will keep its secrets, but not forever. Want to be there when the next mystery unravels? Stick around, hit subscribe, and let's keep exploring the unknown together. Because the universe isn't done surprising us yet, and neither are we.